Every revolution brings the same contact surface back to the process. If a roller carries wear, runout, or contamination, that condition can return at the same rotational frequency. A precision roller therefore acts as more than a support. It becomes a repeating mechanical reference for the material moving across it. A zirconia ceramic roller places a hard, nonmetallic working surface around a rotating shaft. The engineering value is not simply that zirconia is hard. The surface must stay cylindrical, smooth, aligned, and resistant to repeated contact while the shaft continues to carry the roller through every revolution. For the Y-TZP grade listed for this component, Vickers hardness is above 12 gigapascals and flexural strength is listed at 1000 to 1200 megapascals. In a roller, that combination matters because abrasive particles and repeated contact can gradually change the working surface. Slower surface wear helps preserve the diameter and finish that the process relies on. Zirconia also has a toughening mechanism that distinguishes it from many structural ceramics. Around a stressed crack tip, metastable tetragonal grains can transform toward the monoclinic phase. The local transformation creates compressive shielding around the crack and reduces the driving force for further extension. It does not make the ceramic impact-proof, but it improves resistance to crack growth under controlled loading. The working surface is also electrically insulating and chemically stable in many process environments. At contact points where exposed metal is undesirable, a ceramic surface removes bare metal from the rubbing pair. That can be useful when a line is sensitive to conductive debris, corrosion products, or surface marking, although compatibility still depends on the actual chemistry and cleaning method. Once the material is selected, rotational geometry becomes the next constraint. A roller returns to the same angular position once per revolution, so eccentricity creates a periodic disturbance rather than a random one. Research on roll-to-roll coating systems treats eccentric rolls as a measurable fault source because repeated radial error and disturb the process at a characteristic frequency. The listed surface specification is R 0.1 to 0.2 micrometries, with roundness at or below 0.01 mm. Those values should be read as component-specific targets, not universal zirconia standards. In service, surface finish influences how the moving web contacts the roller, while roundness and concentricity determine whether that contact geometry repeats smoothly as the shaft turns. The ceramic and metal portions also have to function as one rotating assembly. Journal diameters, shoulders, bearing seats, the ceramic to metal interface, and axis alignment all affect whether the working surface runs true. A hard ceramic sleeve cannot compensate for a misaligned shaft, and a precise shaft cannot correct a ceramic surface that has been finished off-center. There is no single cross-industry standard size series for zirconia ceramic rollers. The target specification is customizable, which matches how machine rollers are normally defined, by working diameter, face length, shaft journals, bearing interfaces, and the space available inside the host equipment. The machine interface, rather than a generic catalog diameter, sets the dimensional envelope. For a non-standard build, the drawing should define the ceramic working diameter, active face width, overall shaft length, journal diameters and lengths, shoulders, grooves or holes, surface finish, roundness or runout requirement, and allowable speed. The process roll must also be stated because a guide roller, traction roller, calendar roll, and grinding roll are designed around different contact loads. One relevant use is roll-to-roll battery electrode coating, where thin metal foil or coated electrode web passes continuously through multiple rollers. A zirconia ceramic roller can serve at a contact or guiding position when the design calls for a hard, smooth, electrically insulating, nonmetallic working surface. 4 performance priorities become visible in that setting. Stable web contact begins with geometry. The moving electrode web is tension sensitive, and high-precision roll-to-roll systems depend on controlled transport between rollers. A round, concentric roller gives the web a repeatable path. Any eccentricity or misalignment can re-enter the system once per revolution and appear as a periodic disturbance. The wear-resistant surface matters over long production runs. If the roller surface gradually changes through abrasion or scratching, the contact condition changes with it. Zirconia hardness helps the ceramic working surface resist that mechanical change, while the required finish still has to be selected for the needed traction, release behavior, and sensitivity to surface marking. The nonmetallic contact path can also be valuable around thin foils and coated layers that are sensitive to foreign particles. The benefit is not a claim of zero contamination. It is a material choice that removes an exposed metal contact surface from that station. Cleaning chemistry, particulate control, and neighboring components still determine the final cleanliness of the process. Ultimately, a zirconia ceramic roller earns its place by holding two kinds of precision at the same time: material precision at the contact surface and geometric precision around the axis of rotation. When both are engineered for the actual web, load, speed, and interface, the roller becomes a stable reference instead of just another rotating part.